In this video, we're going to learn about reflections. Reflections are often referred to as a mirror image or a flip. They are rigid transformations in which all points of a pre-image are moved over an axis of symmetry. Because we talk about an axis of symmetry so much, I abbreviate it AOS. Notice that axis actually means line, so other ways you can refer to an axis of symmetry are line of symmetry or a reflection line. We typically deal with 4 types of axes of symmetry. Notice that the plural of the word axis is axes with an E in there. So one of those axes of symmetry could be a horizontal line. And when you see horizontal lines, those are when you have y equal to a number. Those are horizontal because y is always the same height, right? So x is always changing. So that's how you have a horizontal line. You could also have a vertical line, and that's when x is equal to a number. And that just means x is constantly the same number, right? So if x is always the same, then y is changing, and that's why you have a vertical line. Really make sure you study that because students often get confused between horizontal line and vertical line. You can also just have a line with a positive or a negative slope. And a positive slope line has a positive slope, and then a negative slope line has a negative slope, like that. So those are the 4 types of axes of symmetry that we're going to deal with. The axis of symmetry is a perpendicular bisector of the segment connecting the pre-image points and their corresponding image points. The symbol for perpendicular is this line, and I just often use a perpendicular bisector symbol like this because bisect means you're cutting it in half, so that's a symbol that I use. A perpendicular bisector is a line passing through the midpoint of a line segment at a 90-degree angle. Note that 90-degree angles and right angles are synonyms. So basically, the axis of symmetry splits the segment connecting the pre-image points to their image points in half at a right angle. Reflections do not maintain orientation. Orientation refers to the arrangement of points relative to one another after a transformation has occurred. It can also be thought of as the order of the points when traveling around a geometric figure. Reflections are the only isometry that do not preserve orientation. Recall that isometry refers to rigid transformations. There are 3 types. We have rotations, translations, and reflections. So reflections are the only ones who don't preserve orientation, meaning that rotations and translations do maintain orientation. Notice with the example we have on the page at the top right that if we were to move around the pre-image, alphabetically is usually how we do it. So if we go A to B to C, we're moving a certain direction, and we're actually moving counterclockwise. So if we go to our image and we go around the same corresponding points, right, with A prime, B prime, C prime, notice in this case we're moving clockwise. So we go from moving counterclockwise to clockwise, and that's what we mean about the orientation not being maintained. If you know a rigid transformation has been applied, and you see that the orientation has changed, most likely you have a reflection. Because reflections are the only rigid transformation that don't preserve orientation. When reflecting over a vertical line, the x value from your coordinate will change and the y value will stay the same. But when you reflect over a horizontal line, however, when reflecting over a horizontal line, the y value will change and the x value will stay the same. If you reflect over the line y equals x, you use the mapping rule, xy goes to yx. That's easy for me to remember because if you're flipping over y equals x, then all you're doing is switching your x and y values. When you reflect over the line y equals negative x, you use the mapping rule xy goes to negative y, negative x. A similar thought process for how to remember that is you're reflecting over y equals negative x, so you're flipping the x and y values, and because you have a negative slope, you change the sign for both of your x and y values. Just like with rotations, we can talk about mapping a figure onto itself through a reflection. We can also call that a carrying a figure onto itself. And so if you're trying to carry a figure onto itself, your goal for reflections is to find the axis of symmetry that will result in the figure mapping onto itself. So take, for instance, the letter B. Assuming that I drew this perfectly symmetrical, we can see that a horizontal axis of symmetry would cause the B to reflect over onto itself, right? Because if you reflect over, this part would map perfectly onto this part and vice versa. Now we're going to do a few example problems. Example 1, reflect the point A, 1, 4 across y equals 0. So whenever you're reflecting something, you need to know what you're reflecting and what you're reflecting over. So you need the point or points and the axis of symmetry. So in this case, we have y equals 0. So how do we know if that's a horizontal line or a vertical line? Y equals 0 is saying that y is always going to be 0. So if y is staying the same, that means x is changing, and that means it's a horizontal line. Y equals 0 is also called the x-axis. Because I'm reflecting over a horizontal line, I'm just going to plot the point I was given, so my pre-image, and the axis of symmetry, and then use those to find my image coordinate. So notice how I draw the axis of symmetry as a dotted line and I label it. That's because I want to make sure I know that the dotted line is how I distinguish that's the axis of symmetry, and labeling really helps me stay clear on what I'm doing. So as we talked about before, the line segment connecting the pre-image point to its image point is bisected by the axis of symmetry. So what that means is it cuts that segment in half. So if I use that to my advantage, I can see that there are 4 units between my pre-image point and the axis of symmetry. And so because that axis of symmetry cuts A to A prime in half, I know that if I go down 4 units, then that's going to be where A prime is located. So A prime is located at 1, -4. And remember that A is located at 1, 4. So notice how when you're reflecting over a horizontal line, your x values stay the same, right? X was 1 for the pre-image, and x is 1 for the image. But notice how your y values change. And it's in relation to the distance between the pre-image and the image with the axis of symmetry. So again, your axis of symmetry is the perpendicular bisector of the line segment joining A to A prime, right? So that's your pre-image coordinate to its corresponding image coordinate. So in red, I'm making the line segment of what I'm talking about. So if you notice here, the point 1, 0 is the midpoint of A prime. And so that means that A to your midpoint is 4 units, and then M to A prime is also 4 units. So that's going to get the idea of the perpendicular bisector. And right here, these angles are 90 degrees. Because we don't have an actual figure that's being reflected, we can't really see anything about the orientation here, but we will see that in the next few examples. Now we're going to see an example of reflecting the same point, but we're going to reflect it across a vertical line. Notice that every time I'm graphing my axis of symmetry, I also include arrows on either end. And that's because the axis of symmetry is a line, so it continues on in both directions, and that's what those arrows signify. I can still use the idea that the perpendicular bisector, the axis of symmetry, is halfway to the pre-image, right? So there's 3 units between the pre-image A and the midpoint on the AOS. So if I just go 3 units in the opposite direction, I'll wind up where A prime is supposed to be. So if you notice, A prime is located right here at -5, 4. So notice how when we reflected across a vertical line, our x values are the ones that changed, but our y values stayed the same. And in this example, we can't really see much about the orientation again because it's just these 2 points. But we can see the difference, or the thing about the perpendicular bisector, right? So if we connect these 2 points, we can see that this point right here is the midpoint because it cuts the segment A prime A in half at a 90-degree angle. In this example, we're going to be reflecting across the line y equals -x, and the triangle was already given to us. So to start our reflection, we have to make sure we graph the line first. So to start this problem, what we need to do first is to graph the axis of symmetry y equals -x. So what that line means, what it's telling us, is that whatever y is, x has the opposite sign. So it's pretty easy for 0, like if y is 0, then x is 0. So we have the point 0, 0 on our line. If y is -1, then x is 1. So we have the point 1, -1 on our line. If y is -2, then x is 2. So we have 2, -2, and so on and so forth. So you can see that it just has a slope of -1. So as we mentioned in the previous slides, we have a mapping rule for reflecting across the line y equals negative x. Now what I'm expecting is because our pre-image is in the first quadrant and it's being reflected over this y equals negative x line, I'm expecting it to be somewhere in the third quadrant. So we'll be able to verify that prediction, but our mapping rule is xy goes to negative y, negative x. So I've labeled all the coordinates for A, B, and C, and so now we just use those coordinates with our mapping rule. So if we start with the pre-image coordinate A, 1, 1 is going to go to negative y, negative x. So we're going to have a coordinate A prime at negative 1, negative 1. Looking at B, we're going to go from 4, 4 to negative 4, negative 4. And with C, we're going to go from 1, 4 to negative 4, negative 1. So looking at this, our prediction was correct. And if we connect our pre-image and our image points, we'll see the same thing we've been seeing all along about the perpendicular bisector. We can also see orientation in this example. So notice that in our pre-image, going from A to B to C, we're moving counterclockwise. But then if we go from A prime, B prime to C prime in our image, we're now going clockwise. So this is the example of our orientation being changed because we go from counterclockwise to clockwise. Our final example is getting a trapezoid, JKLM, to carry on to itself. So we have to find out the axis of symmetry, or the axes of symmetry that will do that for us. Looking at the figure, I can tell that a vertical line is going to have to be the axis of symmetry that we need because that'll make it fold onto itself. So if you think about mapping a figure onto itself, you could just think about having a piece of paper of the figure and then finding out how to crease it so that it perfectly matches onto itself. So notice here I zoomed in and I found the length of side ML. It's 8 units long. So I know the axis of symmetry passes through the midpoint. And so that's going to be 4 units in. It's going to split ML into 2 segments that are 4 units long, right? Because 8 divided by 2 is 4. Now that doesn't mean that our axis of symmetry is x equals 4. It means that we need to move in 4 units from either of the endpoints. So we can move in 1, 2, 3, 4 like that, or you can move in 1, 2, 3, 4 here. Either way works because it's the midpoint, right? So then we can just continue the line, and our axis of symmetry we can see is x equals 2. I guess you could have looked at the other side, JK, and done the same process, but it's easier to work with the shorter side because it's smaller numbers. So what we see is if we were to fold or to reflect this figure across x equals 2, then we would get j to map over here to k, right? So j prime would be here, k prime would map over here, m prime would map here, and l prime would map here. So all the points would wind up on the original figure, but the orientation will have been switched. You have the following 2 questions to answer in your Google form for the check-in for reflections. You need to determine which of the following statements is false, and you're going to determine the axis or axes of symmetry that will make the trapezoid carry onto itself, and you'll select all that apply. So this concludes your notes on reflections. Today's learning targets are I can perform a coordinate reflection and express the reflection with a graph, mapping rule, written description, and function notation. And just like we said with the dilations video, for learning target 1.8, you may not have done all of these today, but you have done a few. And as always, shout out to Slides Carnival for sharing these awesome resources for free for us to use. Thanks for watching.